So how many of you have heard of JPL? Ah, good. Yeah. So it's my great privilege to be part of the only team that will be the first to explore the solar system. The NASA Caltech Jet Propulsion Laboratory, JPL, is the world's premier research and development center for the robotic, that is, unmanned exploration of the solar system. Indeed, Voyager 1 has now left the solar system and is operating in interstellar space. Now, I want each of you to take out your smartphone and make a calendar entry. In 40,000 years, Voyager 1 will drift near a star in the constellation of Camelopardalis, and you will surely wish to be alerted to that event. For your calendar, that will be the year 42,016. I will get back to you later on the month and day. But JPL built the US's first satellite, and if we were number 2 after the Soviet Sputnik, and Australia was number 4 from Woomera, JPL built the first planetary rover and other firsts. I'm a deputy to the JPL chief engineer, as well as serving as the chief knowledge officer, the CKO of JPL. As Ian mentioned, I'm on the board of directors of the 63rd International Reliability and Maintainability Symposium. I've been helping to organize that annual conference for 16 years, so I know about the hard work in planning a conference like this, and I thank my hosts for giving me an opportunity to speak to you. My background is in reliability engineering, astronautical engineering, even though I didn't start out as an engineer. But I spent 20 years as a NASA reliability engineer before I joined the JPL office of the chief engineer. So Ian, I think I probably qualify as one now. I believe this may be the golden age of space exploration. JPL presently has 47 spacecraft missions, either in development or operation. These range from near Earth to interstellar exploration beyond the boundary of our solar system. That is Voyager 1 at a distance of 133 astronomical units, oddly highlighting a few that suggest that humans have a stake in space exploration. And as a chief knowledge officer involved in the KM discipline, I'll make a case that NASA typifies the risk of failing to capture key knowledge. And incidentally, 80% of NASA projects are international partnerships. The JPL Deep Space Network operates an antenna complex in Canberra that includes a 70-meter diameter dish. And we have NASA mission commander Dr. Martha Lenio, a University of South Wales graduate, living in a dome on Mauna Loa volcano in Hawaii to simulate a spaceflight mission to Mars. 2 months ago, NASA and Australia successfully tested a hypersonic rocket capable of flying over 7 times the speed of sound. Yeah. So what are the stakes in space exploration for the US and for our planet? JPL builds and operates spacecraft mainly for the science return, although technology demonstration is sometimes a secondary purpose. The science focuses on the search for life. Hence, we are interested in the surface of Mars and the ice-covered oceans of Europa. Okay, so, but why do we explore? Fear and pride may have a role. Fear, no one in my village has ever gone over the hill, and there may be something over there that can harm us. And pride, I'm the only one in my village that has ever ventured over the hill. But there is also curiosity, which happens to be the name of our most recent Mars rover, currently operating for about 2.5 years. Some things are worth doing because they are worth doing, and not in hope of profit or glory, in spite of their difficulty, but boldly relishing their difficulty. Only when the pursuit of knowledge is unhampered by a desire for short-term gain can we reach our potential and the stars. The Great Pyramids of Giza were engineering marvels, and we're still uncertain how the ancients were able to build them and achieve such precise dimensions, a daunting task for architects even today. But another interesting question is, why did they build them? They were probably meant as tombs for Pharaoh, and the pyramidal shape had religious significance, but the earlier Pharaoh pyramids were built of wood and brick. So why build something so monumental that must have consumed much of Egypt's GNP? It didn't feed their people or make them more secure. I think they did it because it was a great challenge that no one else could accomplish. They did it because it was difficult. So I'm going to show you a modern day equivalent of the pyramids of Giza.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. It just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
Biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about 1/3 of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we're gonna go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. JOI.
Nothing's really certain about what's going to happen.
So nothing is really certain about what's going to happen. To give away the ending to the story, July 4th is celebration of U.S. Independence Day. Now, I don't know if it was done for PR or whether it's just coincidence, but Jupiter orbit insertion was successful on July 4th. But enough of that. Let's take a hard-nosed approach to the question of why do we explore, and look at several business cases for pursuing space science. Goodbye, Earth's atmosphere. High-stakes business case number one. We study the Mars atmosphere. Scientists think Mars, like Earth, may have been a warmer, wetter planet billions of years ago, until something catastrophic happened to its atmosphere. Recent data collected from the MAVEN mission suggests that Mars' atmosphere may have been blown away by coronal mass ejections from the sun. The evidence is that such an ejection in March 2015 was seen to be causing gas ions from Mars' atmosphere to shoot out into space, as you see in the artist's rendition on the left. On the right is a simulation of the effects of a particularly large ejection of the sun's coronal mass upon the Earth's atmosphere. To me, that puts science return in perspective. So what are some of the challenges in studying Mars? The Curiosity rover is a mission you may have heard of. The most recent of 4 rovers, JPL, has successfully landed on Mars. I plan to show you a video in a few minutes that will highlight one of the engineering challenges in the design of this mission. The rover is about the size and mass of a small car, about the size of a Mini Cooper. It uses a nuclear power source instead of solar panels because of the latitudes at which it operates and because the power demands of the instrument suite, including a laser cannon that samples boulders. JPL's goals include finding if Gale Crater had ever had conditions favorable for microbial life. It has already expanded our understanding of Mars' habitability for future human exploration of Mars. On Mars now for 4 years, Curiosity has already completed its primary 2-year mission, and its operation has been extended indefinitely. Plus, a Mars 2020 rover modeled on Curiosity is in development at JPL. We eventually seek to send humans to Mars. Even if Queen Isabella had had the capability to launch robotic ships to the Americas, further exploration would have required humans. The 7 minutes of terror.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skycram maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
The 7 minutes of terror. Going back to the technical challenges posed in building the Great Pyramids of Giza, this video highlights some of the technical challenges related to just achieving a landing on Mars. As you watch the film, I would have liked you to consider two things. First, the engineering challenge in successfully triggering these sequences over the course of 7 minutes after the system has traveled millions of kilometers. And secondly, the KM aspects of the knowledge management impact on JPL's Mars exploration program. If JPL did not have a Mars mission every 5 years or so, would we be able to keep our staff employed? Would we be able to retain the critical knowledge of how to land on Mars? High stakes business case number 2, planetary defense. This is JPL's planned asteroid redirect robotic mission. JPL's plan to snag an asteroid and tow it into near-Earth orbit may also include a planetary defense demonstration, providing the first in-space test of an enhanced gravity tractor, which is where you position a relatively small object, like a spacecraft, close enough to an asteroid for gravity to exert pull on the asteroid and eventually change its trajectory. If you start far enough away from the Earth, you can possibly deflect an asteroid that presents something like the dinosaur killing event. In 1908, a relatively small impact event, as compared to the history of asteroid impacts on Earth, in Tunguska, Siberia, leveled 80 million trees with a force 1,000 times more powerful than the Hiroshima bomb. Such strikes illustrate the possible stakes in demonstrating gravity tractor capabilities. And I would argue that such a capability might be of interest beyond scientists and engineers. The plan is for the ARM project to be combined with a human exploration component in which astronauts would rendezvous with the robotic spacecraft and take samples of the captured asteroid. High stakes business case number 3, other Earths. And this is one of the most fascinating to me. The JPL Kepler mission. The Spacefaring Observatory has detected 21 validated Earth-sized planets orbiting distant stars that are located in the habitable zone, meaning it's the right distance from the sun and the right atmospheric pressure to have liquid water on the surface. And we've seen in some very hostile Earth environments, like the deepest ocean depths, that where you have water and energy, you have life. The first Earth analog found by Kepler, it's named Kepler 186f, resides about 500 light years from Earth in the constellation Cygnus. The Kepler spacecraft has found another 2,200 planets that are not in the habitable zones. But extrapolation from the 9 Earth analogs suggests that the Milky Way has at least 8.8 billion planets, Earth-sized planets, in a solar habitable zone and capable of life. So in addition to the dangers of Earth's atmosphere boiling away, or Earth being struck in a cataclysmic impact event, Space exploration is giving us an opportunity to find Earth-like environments hundreds of light years from us. Lastly, let's take a look at return on investment. Because our investment in space exploration could instead be invested in meeting social needs or something else worthwhile. JPL spaceships in deep space are crewed by robots instead of humans. If Queen Isabella had launched robotic ships, and if the robotic Nina Pinta and Santa Maria had included camera drones, okay, the Spanish could have achieved a decent coastal survey, but would the Spanish have established a presence in the New World with only robotic ships? Or did they need the 15th century equivalent of astronauts? So Queen Isabella had turned down 3 proposals from Christopher Columbus until her personal treasurer pointed out that the proposed budget for Columbus's voyage was less than the cost of entertaining a visiting noble in the court of Seville for 1 week. Also, Spanish aristocrats had value, but common seamen and an Italian skipper were wholly expendable. So she was looking for cheaper pepper, essentially. Maybe in the corner of the market for black pepper from India. But what was the actual return on the investment, on her investment? And perhaps infinite, because she not only discovered a new world, but the inhabitants of the new world are now discovering new worlds. In 2012, NASA headquarters announced a knowledge management initiative and told each of its 10 field centers, that's where the actual NASA engineering work is actually done, not at headquarters, that they should appoint a chief knowledge officer. So JPL's response was, what's a chief knowledge officer? So I told the leadership about knowledge management, and they said, aren't we already doing that? I said, yeah. For example, we've had a lessons learned committee meeting weekly since 1984. But we need to focus attention on retaining critical knowledge, key knowledge. First of all, because if we were to lose key knowledge, it not only would be costly to restore, but also would present additional risk, because the heritage knowledge, we lost, had already been proven in ground test and spaceflight. Then JPL is rather unique. No one else lands on Mars. Obviously, no one else goes to Jupiter or Neptune. I say again, no one else lands on Mars. I mean, other countries have launched 21 missions to Mars, and they've all been failures, except for one Soviet lander that I think lasted 14 minutes on Mars' surface. So if we lost JPL's critical knowledge, for example, how to land on Mars, or how to make spacecraft autonomous because they're cruising too far from Earth-based controllers to correct an error in time, where would JPL go to re-obtain that capability? How can we lose critical knowledge? Today, NASA engineers and scientists over age 50 outnumber those under age 35 by 4 to 1, as compared to 20 years ago when those two groups were equal in number. So we face a silver tsunami of the eventual loss of key employees. Then I pointed out to the leadership that JPL presented some quick wins in which fixing knowledge capture problems could have short-term and outsized benefits. And finally, I pointed out that our NASA overlords in Washington, D.C. had told us to appoint a CKO. And so they responded, hey, that should be you. So the JPL strategic plan places a focus on critical knowledge. Not all knowledge is critical to a company continuing to do what it does best. I mean, JPL makes some of the world's most expensive and most risky products. We make a single unit designed to do the impossible. And if it breaks, we can't send someone to Saturn or Mars to fix it. So engineering knowledge is critical to JPL. Is engineering knowledge critical to, say, Coca-Cola? Coca-Cola makes sugar water. But is marketing knowledge critical to Coca-Cola? I'd say that's their specialty, marketing. So what knowledge is critical to JPL to retain and share internally if it is to continue to explore deep space? Well, JPL spacecraft are often high unit value, often one of a kind. They must operate with precision in an extremely hostile alien environment. Deep impact travel 263 million kilometers at 64,000 miles an hour to hit a small target. And accomplishing that requires what I call extreme engineering, like extreme sport, only it requires a team of nerds. If you watch the Caltech scientists on the Big Bang Theory. Here's where I step up to my soapbox. I'd like to suggest to you that a threat to the continuing success of your company or agency is your ability to make good use of what you know. In some industries, firms invest more in knowledge-based capital than they do in physical capital, such as equipment and buildings. Yet, knowledge is often treated as if it has little or no value in terms of reuse. The Romans used pozzolan concrete to build large structures. Here you see the Pantheon, the Colosseum, Roman baths. But the formula for concrete was lost for 1,000 years until a textbook was discovered in the year 1414. The Romans built Roman baths from England to Turkey, and then the world just forgot how to make large concrete structures. It's even easier for a company to lose the knowledge that's critical to their competitive edge. A key institutional knowledge may be lost unless leadership supports active measures to retain it. And here's a good example. NASA thrusters. They're small rocket engines. The ones used for attitude control, maybe a little larger than my fist. Typically, they fire continuously until they switch off, or they fire in rapid pulses. Why? Because such thrusters are very simple and reliable. But the Mars Science Laboratory descent stage you saw in the 7 Minutes of Terror video, also known as the sky crane, needed descent thrusters or retro rockets where you could adjust the output, like the accelerator pedal in a car varies the engine output. Why? Because the sky crane needed to hover off the surface of Mars while you saw it lowering the rover to the ground. The problem was that JPL had not designed throttleable thrusters since the Mars Viking lander that was designed around the year 1970. We had lost the knowledge of how to design throttleable thrusters. Fortunately, we found some retirees from the Viking project we could interview, and they were able to help us. But we failed back then, as an institution, to retain that knowledge. So lastly, what can you do, or your company do, to manage critical knowledge more effectively? First, there has to be commitment on the part of senior management to preserving critical knowledge as a valuable resource. Too often we treat knowledge as if it has no residual value after we first use it. Then, because you can't effectively preserve all knowledge, you need to determine what's really critical to preserve. Right? But your company probably already conducts activities like seminars to share knowledge. So you need to identify gaps and maybe lessons learned program. So you need to identify gaps in capturing, retaining, and sharing it, and implement activities needed to address the gaps. There are many best practices that are used in industry. I mentioned JPL has a lessons learned committee that's met weekly since 1984. There is mentoring of junior employees by senior employees. The U.S. military has long had a practice of filing after action reports. I'm sure Barry can tell us about the Irish after each battle, it outlines what they did right and what they did wrong. Pause and Learn is a NASA version in which peers, a set of project managers, can share stories about how they solved the problem. And you can't tell if you're being effective in preserving key knowledge unless you collect data. So, like engineers at JPL, you're doing challenging work and taking risks. So it behooves you to act as a champion, a knowledge champion, and to encourage your coworkers to champion the retention and sharing of knowledge that may be reusable, to make good use of what your company knows. So what's at stake? That's where we started off. Why do we explore? Humanity's interest in the heavens has been universal and enduring. Ancient civilizations speculated about the cosmos, and our early scientific efforts focused on astronomy. Humans are driven to explore the unknown, discover new worlds, and push the boundaries of our scientific and technical limits, and then push further. Space exploration helps us to address fundamental questions about our place in the universe. Are we alone? Might earthbound humanity expand beyond its current limits? This is the first photograph of our home taken from another world. It was taken from lunar orbit on December 24th, 1968 by astronaut William Anders during the Apollo 8 mission, the first manned mission to orbit the moon. Later in the Apollo program, there were amazing images of astronauts walking on the moon, but there's no underestimating the impact of this photo when it was first seen worldwide. A common expression during the 1930s was, "That is as crazy as going to the moon." It was this photo, looking back at the Earth from the perspective of another land, that not only changed what was considered crazy, but gave humans a new understanding of who we are and perhaps who we might become. Thank you.